Hello class, this is the PowerPoint presentation for the review class for test 3. I skipped first of the few slides where I discussed, where I listed all the syllabus and the learning objectives. You can get that PowerPoint file from your Canvas, so use that one. And now in this video, I will go through the practice problems steps so that you can start working on that. So for the very first one, a 6 horsepower pump with a 6-inch diameter hose is used to drain water from a large cavity at B. Determine the discharge at C, neglect friction losses and the efficiency of pump. Okay, so they are asking you to find the discharge at C, QC, and you have a pump here, a few surfaces here, so you need to use the energy equation here. But the good thing is they said that neglect friction loss, so there is no loss in the system here, or it's very insignificant. So for energy equation you need 2 points at which in between which you will apply the energy equation. So B and C, they can be good choice of points because at B pressure and velocity can be 0 and at C the pressure can be 0, so at least few terms will be 0 here. So let's write down the equation first in between B and C. So it will be PB over gamma VB square over 2G and CB each pump and PC square over gamma, PC over gamma, VC square over 2G, GC, and the head loss is 0. So what we will do now, P is 0, V is 0 here, PC is 0, head loss is 0, and we need to find we need to set a datum so that we can get the ZB and ZC. So you can set this one as datum. So ZB will be 0 but ZC will be 3 meter. So basically you are having each pump VC square over 2G plus 3. Okay, now here we have two unknowns, VC and each pump. Since we need QC, so VC multiplied by AC, we can work with that way. But VC unknown. From this equation, again VC unknown and the H pump is unknown. So what we can do, we have another given value here, a 6 horsepower pump, which is the pump power. So you can actually say that power equals to gamma Q H pump here, and the power is 6 horsepower, but you can't work with 6 horsepower, so it will be 6 550 since it's water, so you can say 62.4. You can keep that as Q, or you can say it's AV and horse pump. Okay, now you can find A, so the horse pump will be some number over V, and you can use that here. So you have everything in terms of V, find V and then find Q. Okay, so that is question number 1. So question number 2, it says that the solution is ejected from the 20 millimeter diameter syringe through a 0.4 diameter needle. If the pressure developed with the syringe is assumed to be constant at 50 kPa, determine the velocity of the solution through the needle, and the maximum height of the liquid rises in the air. Okay, so you need to calculate the velocity at that point and H max. So what we can do, let's name that this one is A, this one is B. So basically you need to calculate VB and H max. Okay, so what you can do, we have 2 points. Again, we can apply the Bernoulli's equation because they didn't say anything about the loss. So we can say that we can apply the Bernoulli's equation. So what you can do, apply the Bernoulli's equation between A and B. So PA over gamma VA square over 2G and PB over gamma VB square over 2G and CB. Okay, from here we will try to find the VB. At PA, it's given if the pressure developed within the syringe assumed. So PA is 50 Pascal. Okay, at VA, here assume the velocity through the needle is much greater than through the syringe. So that simply says you that at A the velocity is very less than the VB. That means VA VB. So you can consider that as kind of 0. And at PB it's open to atmosphere, so again that is 0. And VB, that's what we are trying to find. And the ZB, that can be 50 over 1000, provided you are using this one as the data, right? So you have ZA is 0, so you have this one, and you can find the VB from this calculation. Now the next part, how can you find the H max? So you can consider this point, you can name this point as C, and you can apply the Bernoulli's equation at A and C. So it will be PA over gamma VA square over 2G ZA and PC over gamma VC square over 2G VC. Now again PA, you know that 50 kilopascal. The velocity is almost 0. PC, it's open to atmosphere, it's 0. Now VC, the velocity at C will be 0 here because when the velocity is 0, that's when the fluid will stop moving, and that is the maximum height here. Okay, so this will be 0 also. So what you basically have here is actually the ZC will be the H max and ZA will be 0. So you whatever you have here, H max is actually the that is the value for the H max. Okay, so that is question number 2. And so let's move to the next one here. Question number test review 3. Okay, this one. So water from a faucet tapers from a diameter of 4.5 inch to 0.3 inch after falling 10 inch. Determine the velocity of the water at A and B. This is the most simplest one you can have. So you will just apply the Bernoulli's equation in between A and B. Okay, so it will be PA over gamma V A square over 2G ZA and PB over gamma VB square over 2G and ZB. Now PA and PB both are open to atmosphere, so that can be 0, 0. And VA and VB, which you don't know right now, but ZA and ZB. So what you can do, we said that we will always use the lowest possible point to datum as a datum. So this one is datum, and your ZA can be 10" and ZAB can be 0. Now you see you have VA squared 10" and VB squared over 2G, so that is kind of two unknowns, and you have only one equation, so that means you need one more equation. What you can do, for A and B you know the area but you don't know the velocity, but what you can say that QA equals to QB because there is no other inlet outlets here. So AAVA, AAAB, and you can find something like this way, or you can express this one as in terms of express for VB, and then use this value here, and finally you can calculate the VB. Once you know the VB, you can calculate VA. Okay, so question number 4. Here the pump is used with a 3-inch diameter hose to draw the water from the cavity. If the discharge is 1.5 cubic feet per second, determine the required power developed by the pump. Frictional head losses in the hose is 1.5 feet for every 20 feet of the hose. The hose has a total length of 130 feet. Okay, so what again, this one is pretty much similar to the very first problem. You need to apply the energy equation between B and C. For the question number 1, there was no head loss or frictional loss, but here we have some frictional loss, so we have to consider that. So pressure is 0, velocity is 0, ZB is 0 plus pump head, and for C, pressure is 0 but velocity is not 0. ZC is 3 plus head loss. Okay, so pump head, since you need to know the determinant of required power developed by the pump, so basically we are trying to find pump head, and for VC you have the Q, you can calculate the area, that is your VC, and for head loss it says that 1.5 feet for every 20 feet. So that means 1.5 feet for every 20 feet multiplied with it says that the hose has a total length of 130 feet. So in between B and C, you can consider the total length as 130 feet here. For one of your homework, I think I said you can deduct the 8 feet because from A to C should be the total length of the hose. You can do that here also. It will not change that much. So you can use 130 or 120, 122. Okay, so once you have the head pump, then you can say the power be gamma head pump and the Q. So you know gamma, you can find the head pump and Q. That will be question number 4. Okay, so question number 5, draw EGL and HGL for pipe ACB. You have pump head 17.8, velocity of the pipe 10.19, pressure at inlet at 30 kPa, and the pressure at B. So what you will do for this one, you need to draw the EGL and HGL. EGL and HGL means energy grid line and hydraulic grid line. So what you can do, you can draw some line here, AC, B, and you can start with EGL, because I think for velocity at inlet. So okay, so velocity of the pipe and pressure at inlet. So you know the pressure, velocity, and Z for A. So what you can do for A, the EGL will be PA over gamma, VA square over 2G, and ZA. So the velocity of that pipe is 10.19, and the pressure at inlet is negative 35 kilopascal. So you need to convert that into Pascal, and it's negative, so it will be negative 35 10 to the power 3. You know the gamma, and if you consider this one as a datum, the ZA is 0, so you will get something, and that will be the line up to this point. Okay, and at this point there is a pump head 17.8, so you will add that 17.8 here, so that is the EGL. Okay, and now that part is done. Now for the HGL, we know HGL is like the EGL and HGL are connected that way. Okay, and what you can do, either you can calculate this one, P over gamma plus C. Either you can calculate the HGL at any point because you know the pressure at A and B, but you don't know the pressure at C. So it will be easier if you just subtract the V square over 2G from EGL, because at any point the velocity will be same, as the same flow is going through the pipe and the diameter is same. So you can just use this portion and draw a line just below that. Okay, and you need to add the value here. Okay, so question number 6, it says that kerosene flows into a 4 feet diameter cylindrical tank through pipes A and B with the velocities 2 feet per second, 3 feet per second. It exits at C with a velocity of 1 feet per second. Determine the time required to fill the tank if Y is 0 when time is 0. Ignore the effect of the gravity of the falling kerosene. Okay, so this problem is interesting. So for this one, what they are asking, you have a tank here, you have one inflow A, another inflow B. At the same time, you have one outflow at C. That means water, like the kerosene, like for this setup we have 2 inlets, 1 outlets, and obviously whether the tank will be filled with kerosene or not, it will depend on the what amount of flow is coming and what is going outside. So they are asking you to find what is the time required to fill this tank. Okay, so to do that we need to know what amount of water is actually remaining here at every second or every minute or something like that. So what you can do, you can find out the like incoming flow A plus B. Okay, so QA plus QB, outgoing flow QC, and here the storage per second will be QA plus QB minus QC. That is the storage per second. Okay, so each second that amount of water is stored in this tank. Now obviously this tank has a certain volume. So what you can do, you can storage per second, that should be in meter cube here. Okay, sorry, feet cube, that should be feet cube here. So what you can do, you will calculate the volume of the tank. This is most probably a cylindrical, yes, so pi r square h. Okay, so it will be some value. Now the one you got here, the feet cube per second, you can say that to fill that amount of that feet cube of container required time 1 second. So to fill that pi r square h container, what will be the required time? That's what you need to find. Okay, so you can do that. The answer is 7.19 minutes. So you need to convert your answer into minute for this one. Okay, so this is review Q6. For Q7, that is easy also. The jet engine draws in air at 18 kg per second and jet fuel at 0.916 kg per second. Notice the unit, it's kg per second, so it's mass flow rate. Okay, here if the density of the air fuel mixture at the exhaust is 3.36 kg per meter cube, determine the velocity of the exhaust relative to the plane. The exhaust nozzle has a diameter of 0.8 meter. Okay, so this one is, you have 1 point engine the jet engine draws in air at 1800 kg per second, and the jet fuel. Okay, so here that is the fuel which is 0.916. Here it's air, it is 1 kg per second, and this one is the exhaust, okay, which is 3.36 kg per meter cube. So what you can do, obviously it's mass flow rate, and since you are working with air, so it's always better to work with this one, like rho AV outlet, or like incoming flow, outgoing flow. So here if you just look at the direction, it can be just the exhaust, and this can be airflow plus jet fuel. So this one is rho AV. You know most of the things. So for exhaust, you know the 3.36. For Determine the velocity of the exhaust relative to the plane. So what you can do, oh no, you actually, that is actually the density. Okay, so this one will be like 3.36. You can find the area and the velocity of exhaust, and here airflow is 1800 and jet fuel is 0.916. And now from here you can actually find the exhaust. Okay, so up to this point all the problems were about mass flow and the or mass conservation or energy conservation. Now the next three problems will be all about the momentum equation or momentum conservation, linear and angular. So let's work with the question number 8. It says that water flows through the hose with a velocity of 3 meter per second. Okay, this one is 3 meter per second. Determine the force F on the semi-cylindrical cup if it is moving to the right at 2.5 meter per second. Okay, so this cup is actually moving in the right at 2.5 meter per second also. Now for momentum equation, we said that we will always draw two diagram. One is the control volume and one is for all the free body diagram. So here the control body will be like this one. Okay, so this is the control volume, C, B, sorry, C, D and B. Okay, and these are the velocity, and this plate, this one is like this blade, I guess, semi-cylindrical cup. They have a velocity here at 2.5. So what velocity fluid is moving, the plate is moving also, so you need to find the relative velocity, just like one example we discussed in the class. So that is the control volume, and we will draw this one again just to know the free body diagram. So here that is the F. Is there anything they said about the weight of the water? They didn't say anything about the weight of the water, and at this point pressure is zero, so there is no other force. This one is the free body diagram. Okay, now this problem, as I said, we need to work with the relative velocity first. So what you can do, the relative velocity will be water flows through the hose with a velocity of 3 meter per second, and we need to know water flows through the hose with a velocity of 3 meter per second. So here the velocity at 3, so we don't know anything about B. We need to find out what is the velocity at B. So what you can do, QA equals to QB, that means VA, VBAB. From there you can find VB. Okay, and the VB, it's something around 19. You need to calculate that, what will be the exact answer. So the relative velocity can be 19 because B is going this direction and the plate is moving in this direction also. So that will be the velocity of like the relative velocity. Okay, So that is one thing. Now we need to determine the force F on the semi-cylindrical cup. So F is, this is in x direction. So you need to work with x direction. Okay, so that's what we will do. I will move to the next slide and I will draw that again. This is F and the relative velocity was 19 minus 3, which is kind of 16, okay, meter per second in this direction. Okay, and you have F here, and due to this velocity, relative discharge will be obviously AB and multiplied with that 16. That can be the relative, or you can actually calculate for each part what will be the discharge. We will do that later. Okay, so now you have that. What you can do, for Fx, the equation is summation of rho, at first V, rho and Q. Okay, so it will be V FCS rho and Q, right? That's the Q I was talking about, that you need to calculate the relative Q here. Okay, so for Fx, we said that for Fx, we will always use the free body diagram, and for this part, we will use the control volume diagram. So for free body diagram, if you look at this picture, you have only the negative F, nothing else. And here you have V FCS rho Q outlet minus V FCS rho Q inlet. Now you have two outlets, C and D, so V FCS C D and P. Now our next task is we need to find what is rho, what is Q, and what is FCS, right? Now FCS here, the relative velocity 16, that is actually the FCS. So you can use that one. Sorry, that should be for this one at B. Now we don't know the velocity for C and D. So how can we work on that? To do that, you can actually apply the Bernoulli's equation between B and C and B and D, and you will see that in between B and C, the elevation gap is very negligible and the pressure is 0, 0. So basically you will come up with the same velocity at B and C. Okay, so I'm just writing here. So it will be 0 for pressure, VB square over 2G, Z for 0 for Z, 0 plus. So basically you are having VB equals to VC. Same way you will have BB equals to VD. So you can actually apply the same 16, 16 in all the cases. You know the density, it's water, and now you need to know the Q. So what you can do here, the QB equals to QC plus QD. So you can apply that relation here, and that will give you the final F. So this question, I chose this question because it actually consists of lots of things. You need to apply energy equation, you need to apply momentum equation, you need to apply mass conservation. So it is kind of a good package to do all the calculation for this one. Okay, now two more questions, question number 9 and 10. So for this one, they said that water flows through 200 millimeter diameter pipe bend with a velocity of 8 meter per second, and discharges into the atmosphere at B. Okay, so here the velocity is 8 meter per second. Determine the horizontal and vertical component of the force and the moment acting on the coupling at A. The mass of the pipe bend and the water within it is 25 kg, having a center of gravity. Okay, here it's water 25 kg, 9.81. Okay, so they're saying at this point, at point A, you need to find all the reactions and the moment. So what you can do, you can say this one is AX, you can say this one is AY, and since water is coming through this way, this whole thing, they will try to create a moment in this direction. Okay, so you need to find AX, AY, and MA. Okay, so for finding MA, you need to know the pressure force here or something, like at B, because that will create a moment around A. So let's work with AX and AY first. So if you draw the control volume, okay, water is coming through this way, VA, and this one is VB, and since diameter didn't change, so the VA and VB will be same, right? So you can use the VA and VB, that's same, and you can also calculate QA, QB equals to AA, VA, AB, VB. Okay, that is the Q. Now for this one, you have one component here, one component here, and that is VB cosine 60. This one is VB sine 60. Okay, so that is one part. And now you need the free body diagram, which is so for free body diagram, you have AX, AY, and is there any pressure? So at this point, pressure is 0, so which is good. We don't have any other forces here except that AX, AY. So what you can do for Fx, it will be summation of VFCS rho Q. Okay, so for Fx you have only let's check, you have only AX here, and here you have VFCS rho Q out minus VFCS rho Q inlet. Okay. Now VFCS is obviously x direction here, so you need to calculate the V for inlet. You already have the VA. For outlet, you need to take that VB cosine 60. Okay, and that Q in and Q out is exactly same, you know that, so you can calculate AX. In similar fashion you can calculate AY. Now the next thing is how can you calculate M around A. Okay, so you have weight, which is 25 times 9.81. Okay, so for calculation of moment, if you consider clockwise anti-clockwise as a positive one, so this AY, it's not giving any moment around A, so AY multiplied with 0. Now the W is actually giving a moment here. So actually, you know what you need to do here, we need to consider this one, that W, at the same time we need to apply the because they're like this here, this that will actually create a moment, so due to that flow. So what we will do, we need to add that one as well. So what you will do, you will add the 25 9.81 and that distance for 50 over 1000. And now for this part we need to get the moment, which is R times V rho Q, summation of that. Okay, now for this one, since again we are working with just 1D here, so this vector product will convert into the scalar product, and you can say R multiplied with V rho Q outlet minus R V rho Q inlet. Okay, so the R will be like 0.6 here, and you know the velocity, you know the rho and Q, and that's how you can actually calculate the total MA, what will be the total MA for this one. Okay, so that's how you can work on the Q9. And we have one more problem we need to solve, which is question number 10. So for question number 10, it is kind of the same, but this time the area is changing here, so the velocity will be changed. So water flows through the pipe with a velocity of 5 feet per second. Determine the horizontal and vertical component of the force and the moment at A needed to hold the elbow in place. Neglect the weight of the elbow and the water within that air. Okay, so here determine the horizontal and vertical component of the force. So what we need to do, we need to find the AY and AX, and the water will create the moment in that way. So we need to calculate this moment also. Okay, moment at A. So for AX and AY, uh, we need to, oh, that is actually at A here. Okay, so at this point we need to find the pressure also, and after that we can draw the free body diagram. So at first calculate, draw the control volume here. Okay, so water is coming here, is coming out here. One thing is good about this problem is we don't need to take any components because everything is in either x or y direction, which is good. So V in, V out, and if you want to do the free body diagram, okay, so for free body diagram at A we don't know the pressure, so we need to calculate the pressure here, and here PB is 0, which is good. And we don't have any we don't need to consider the weight of the elbow and the water, so which is good. So that means the only pressure we have here is only external force we have here is like that AY, AX, and this one. Okay, so for the V out, what you can do, you can say QA equals to QB. So AAVA, AVVB, that will give you the VB. Okay, and you need to know the pressure. So what you can do, you can apply the energy equation between A and B. So at A you don't know the pressure, you know the velocity, which is 5, and ZA, PB gamma, which is 0, VB square over 2G, you know the velocity, and ZB. So Z, if you consider ZA and ZB, is there any okay, so they didn't give you the elevation difference between that, so we will we will consider that the elevation difference is very negligible, and so you can say that though that both of these are kind of 0. Okay, so now you can get the value for PA. Okay, so you have PA, PB. Now you need to calculate AY, AX, and MA. Okay, and I will just draw that again. This is the FP, P1 or PAAA, and you have just AX and AY. Okay, that is the free body diagram. And for control volume you have VA, VB. So you can calculate Fx here, and for Fx you have only AX and FPA. Okay, so you have AX plus FP1 this one. For AY, you have only AY, nothing else. And for the momentum here, that should be summation of this one. Okay, so you have one inlet, one outlet, and you're taking moment about A. So for A, that AY will be, at least one force will be 0. So let's work on that. What will be that? The rho and the Q, and in between these 2 points only this V will give you something. Okay, so the R V rho Q outlet, R V rho Q inlet. So inlet is actually the A here, because that is the inlet and B is the outlet. And since you're trying to take the moment around A, the inlet will be the 0. Only thing you will have is for that one, and that's how you can calculate the MA. Okay, so this was the quick review for all the practice problems. I tried to go through the steps, but obviously you will have questions. If you have any questions, just email me or stop by tomorrow and we can discuss more. Thank you, class. I will see you on Wednesday.